Close your eyes for a moment and imagine discovering a new planet. Not just any planet. We're talking about an alien world circling a distant star in the vast cosmic ocean. It might sound like something straight out of science fiction, but this is very much our reality today. Astronomers have developed extraordinary techniques that allow us to find these distant worlds, pushing the boundaries of human ingenuity and technological advancement. Some of these methods are so clever and sophisticated that they'll completely transform your understanding of what's possible in modern astronomy. Right this very moment, as you're reading these words, an intricate network of telescopes, both on Earth's surface and orbiting in space, are actively scanning the cosmos, using methods that would seem like pure magic to our ancestors. Through these remarkable technologies, scientists have already confirmed the existence of over 5,000 exoplanets, with thousands more candidates awaiting verification. Even more astounding is the fact that some of these distant worlds show potential signs of habitability. They might harbor the conditions necessary for life as we know it. But here's the mind-bending part. We can't actually see most of these planets directly through our telescopes. They're simply too far away and too dim compared to their parent stars. So how do astronomers manage to find and study these elusive worlds? The answer lies in a set of ingenious detection methods that leverage our understanding of physics, light, and gravity to reveal these hidden planets. Think about it. We're able to detect objects that are hundreds or even thousands of light years away, objects so distant that the light we're analyzing from them began its journey before human civilization had even invented the telescope. This isn't just science. It's one of humanity's greatest achievements in our quest to understand our place in the cosmos. In the following sections, we'll dive deep into these fascinating detection techniques, exploring how astronomers have turned seemingly impossible challenges into solvable puzzles. From watching for tiny dips in starlight to measuring the subtle gravitational dance between stars and their planets, each method represents a triumph of human innovation and scientific thinking. Let me take you on this journey to understand how we've become capable of finding new worlds in the vastness of space. The techniques we're about to explore aren't just changing our understanding of the universe, they're rewriting the story of our cosmic neighborhood and our place within it. Imagine you're standing on your porch late at night, observing a bright street lamp across the road. If a moth flutters past the lamp, you might notice a subtle dimming of the light, almost imperceptible, but definitely there. This simple, everyday observation perfectly illustrates the fundamental principle behind one of astronomy's most successful planet-hunting techniques, the transit method. The transit method operates on a remarkably straightforward principle. When a planet passes between its star and our point of observation, it blocks a tiny portion of the star's light. This creates a miniature eclipse, causing a measurable dip in the star's brightness. These dips occur regularly as the planet continues its orbit, allowing astronomers to confirm their observations through repeated measurements. Dr. Sarah Seeger from MIT, a pioneering figure in exoplanet detection, has extensively documented how incredibly subtle these brightness changes can be. According to her research, most planetary transits cause a brightness reduction of less than 1% of the star's total luminosity. For Earth-sized planets, the dimming can be as minute as 0.01%. This requires extraordinarily sensitive detection equipment and sophisticated data analysis techniques to distinguish genuine planetary transits from other stellar variations. The most dramatic demonstration of this method's effectiveness came from NASA's Kepler Space Telescope mission. From its launch in 2009 until the end of its primary mission, Kepler revolutionized our understanding of planetary systems by discovering over 2,600 confirmed exoplanets, more than two-thirds of all known exoplanets at that time. The telescope achieved this by continuously monitoring approximately 150,000 stars in a fixed patch of sky, looking for these telltale drops in brightness. The transit method offers several unique advantages. It can detect relatively small planets, even down to Earth size and smaller. It provides information about the planet's size and orbital period. It can potentially reveal information about a planet's atmosphere when combined with spectroscopic analysis. However, the method also has important limitations. The planet's orbit must be aligned with our line of sight. It requires multiple observations over extended periods to confirm discoveries. It works best for planets orbiting relatively close to their stars. It can be affected by stellar variability and other astronomical phenomena. Today, the transit method continues to be at the forefront of exoplanet discovery through missions like TESS and the European Space Agency's CHEOPS. These modern telescopes build upon Kepler's legacy, using improved technology and targeting different types of stars to expand our catalogue of known exoplanets. The next generation of space telescopes, including the recently launched James Webb Space Telescope, will use enhanced versions of the transit method not just to find new planets, but to study their atmospheres in unprecedented detail. This could potentially lead to the detection of biosignatures, chemical signs of life, on distant worlds. The transit method stands as a testament to human ingenuity, turning a simple observation about light and shadows into a powerful tool for discovering new worlds. As our technology continues to improve, this method will undoubtedly play a crucial role in answering one of humanity's most profound questions. Are we alone in the universe? Did you know that stars don't stay perfectly still in space? In fact, they perform an intricate gravitational dance, pulled by the planets orbiting around them. This celestial choreography forms the basis of one of our most powerful methods for detecting exoplanets, the radial velocity method, also known as Doppler spectroscopy. When a planet orbits a star, both bodies actually orbit around their common center of mass. The star's motion manifests as a slight wobble, a back-and-forth movement that can be detected from Earth through precise measurements of the star's spectrum. This wobble creates what astronomers call a Doppler shift. When the star moves toward Earth, its light waves are compressed, blue shifted, and when it moves away, they're stretched, red shifted. The precision required to detect stellar wobbles through the radial velocity method is truly extraordinary. For Jupiter-sized planets, the detectable radial velocity is around 12 meters per second, while for Earth-sized planets, this value drops dramatically to just 9 centimeters per second. Modern spectrographs, such as those used in cutting-edge astronomy, can detect velocities as small as 1 meter per second. The espresso spectrograph at the Very Large Telescope sets an even higher standard, achieving a precision of 10 centimeters per second, pushing the boundaries of what's possible in exoplanet detection. This method offers several key advantages. It can determine a planet's mass, unlike the transit method, which focuses primarily on size. It also reveals critical details about a planet's orbital parameters, such as eccentricity and orbital period. Additionally, the radial velocity method can detect multiple planets within the same system by analyzing the complex patterns of stellar wobble. However, this method is not without its challenges. Stellar activity, such as spots or pulsations, can create false signals that mimic planetary effects. The method is most effective when observing systems edge-on to our line of sight, limiting its application. It also requires multiple long-term observations to confirm findings and works best with quiet, stable stars, making it less effective for more active stellar types. The radial velocity method is historically significant, having led to the first confirmed detection of an exoplanet orbiting a Sun-like star. This discovery of 51 Pegasi b in 1995 by Michel Mayor and Didier Queloz revolutionized astronomy and earned the pair the 2019 Nobel Prize in Physics. This milestone opened the door to modern exoplanet research and demonstrated the immense potential of this technique. Advanced instruments like high-accuracy Radial Velocity, Planet Searcher, Espresso, and the Keck HIRES spectrograph continue to refine the method, allowing astronomers to detect smaller and more distant planets. These instruments have revolutionized the field by achieving previously unattainable precision levels. The magnitude of a star's wobble depends on factors such as the planet's mass, with larger planets creating more pronounced effects. Orbital distance plays a role, as closer planets induce stronger wobbles, while the star's own mass and the inclination of the orbital plane further influence the measurements. Future prospects for the radial velocity method are bright, with next-generation spectrographs being developed to achieve even greater precision. Instruments like the ELT's HIRES spectrograph aim to detect Earth-mass planets in habitable zones around Sun-like stars by reducing detection thresholds below 10 centimeters per second. Additionally, the synergy between the radial velocity method and other techniques, particularly the transit method, enhances its effectiveness. While the transit method provides information about a planet's size, the radial velocity method reveals its mass. Together, these methods enable astronomers to calculate planetary density, determining whether a planet is rocky, gaseous, or a hybrid. This complementary approach provides a comprehensive view of distant worlds and significantly enhances our understanding of their composition and habitability potential. This cosmic dance between stars and their planets continues to reveal new worlds and expand our understanding of planetary systems throughout the galaxy, proving that sometimes the most telling evidence comes not from what we can see directly, but from the subtle movements of the visible partner in an invisible dance. Astrometry stands as one of astronomy's most elegant approaches to exoplanet detection, operating like a cosmic detective agency. This sophisticated method involves tracking the incredibly precise positions of stars in the night sky, watching for subtle shifts that could reveal the presence of unseen planetary companions. At its core, astrometry relies on the same fundamental principle as the radial velocity method. Stars and planets orbit around their common center of mass. However, instead of measuring the star's motion along our line of sight, astrometry tracks the star's apparent motion across the sky, its proper motion. When a planet orbits a star, it causes the star to trace a tiny ellipse in space. The level of precision required for astrometric measurements is extraordinary, with changes in stellar position often as small as milliarc seconds. To put this in perspective, a milliarc second is equivalent to observing a quarter on the Moon's surface from Earth. Modern instruments must measure angles as small as 1/1000th of an arc second, demanding technological innovation and extreme stability. These measurements also require repeated observations over extended periods to confirm planetary signatures. The European Space Agency's Gaia telescope marks a revolutionary step forward in astrometric capabilities. Gaia is currently mapping over 1.8 billion celestial objects, achieving position measurements with unprecedented accuracy. By constructing a three-dimensional map of our galaxy, Gaia is expected to detect thousands of new exoplanets. Its precise data on stellar distances and proper motions provides invaluable insights for both exoplanet detection and broader astrophysical studies. Astrometry offers several unique advantages. Unlike transit or radial velocity methods, it can detect planets regardless of the orbital plane's orientation. This method directly measures planetary mass and excels at identifying massive planets in wide orbits. Additionally, it is effective for planets around active stars, where other methods struggle, and it allows for the determination of complete three-dimensional orbital parameters, offering a comprehensive understanding of planetary systems. However, Astrometry is not without its challenges. It requires extremely precise and long-term measurements, making it more effective for nearby stars than distant ones. Ground-based observations are limited by atmospheric distortion, and while space-based instruments mitigate this issue, they are still constrained by current technological limits. Astrometry also tends to be most sensitive to massive planets in wide orbits, potentially missing smaller, closer planets. Historically, astrometry has been challenging to implement, but advances in technology are unlocking its potential. Nobel laureate Michel Mayor highlights astrometry's importance for future discoveries, as next-generation telescopes and observatories are poised to make this method a cornerstone of exoplanet research. Projects like Gaia, NEAT, and conceptual missions such as SIM represent the future of astrometric exploration, alongside ground-based interferometers and extremely large telescopes. Beyond exoplanet detection, astrometry provides critical data on stellar distances, star cluster memberships, and galactic structure. It also contributes to understanding proper motions of celestial objects and binary star system dynamics, expanding its utility across astrophysics. Astrometry works synergistically with other detection methods, offering unique orbital parameters that complement transit and radial velocity data. It can confirm exoplanet discoveries made through other methods and resolve ambiguities in planetary system configurations. This comprehensive approach enables more detailed characterization of planetary systems, enhancing our understanding of their architecture and evolution. This method is particularly valuable for uncovering long-period planets, identifying multiple planet systems, and determining absolute planetary masses. By studying these aspects, astrometry significantly contributes to our understanding of planetary system evolution and architecture, ensuring its place as a vital tool in unraveling the mysteries of distant worlds. As our technology continues to improve, astrometry is poised to become an increasingly powerful tool in our planet-hunting arsenal. Its ability to provide complete three-dimensional orbital solutions and absolute planetary masses makes it an invaluable complement to other detection methods, helping us build a more complete picture of planetary systems throughout our galaxy. One of Albert Einstein's most profound predictions from his general theory of relativity was that massive objects can bend light. This phenomenon, known as gravitational lensing, has become an extraordinary tool in modern astronomy, particularly in its micro form for detecting distant exoplanets. The method leverages Einstein's brilliant insight that gravity doesn't just affect matter, it warps the very fabric of space-time itself. Gravitational microlensing occurs when two stars align from Earth's perspective, with the gravity of the foreground star, lens star, acting as a magnifying glass that bends and amplifies the light from the background star, source star. This cosmic phenomenon creates a characteristic brightening pattern detectable by astronomers. When the lens star hosts a planet, the planet's gravity adds a subtle yet detectable blip in the brightening pattern, revealing vital information about the planet's mass, distance from its star, and orbital parameters. The microlensing signal is notable for its unique characteristics. Events last from weeks to months, with magnifications that can brighten stars by hundreds of times. Each event is unique and cannot be repeated, with planetary signatures appearing as brief anomalies lasting hours to days within the main event. This makes microlensing both a powerful and fleeting method for studying distant planets. Microlensing offers several advantages. It can detect planets thousands of light years away, including Earth-mass planets and those in the habitable zone. This method excels at finding planets around faint or dark stars and is uniquely capable of detecting free-floating planets not bound to any star. However, it has limitations. Events are unpredictable and unrepeatable, requiring precise star alignments. Follow-up observations are often impossible, and the method provides limited planetary details, necessitating constant monitoring of vast star fields. Current programs like optical gravitational lensing experiment, microlensing observations in astrophysics, and Korea Microlensing Telescope Network lead microlensing research, with NASA's upcoming Roman Space Telescope poised to revolutionize the field. These programs have already yielded groundbreaking discoveries, such as planets in the galactic bulge, free-floating planets, and evidence of planets around low-mass stars. Microlensing surveys rely on global telescope networks to overcome the unpredictability of events. Continuous monitoring is essential, as weather and day-night cycles can interrupt observations at individual sites. Distributed telescopes in different time zones ensure round-the-clock coverage, enhancing data quality and event detection. Statistical insights from microlensing surveys reveal that planets are common around low-mass stars, free-floating planets exist in significant numbers, and cold planets are more abundant than hot ones. These findings underscore the ubiquity and diversity of planetary systems across the galaxy. Looking ahead, the future of gravitational microlensing is promising. The Roman Space Telescope will conduct dedicated microlensing surveys, while improved alert systems and machine learning techniques will enhance event identification and coordination. Advances in modeling will allow for more detailed analyses of microlensing events, further enriching our understanding of distant planetary systems. Microlensing has transformed our knowledge of planetary systems, offering a unique lens into worlds inaccessible by other methods. It has revealed the prevalence of planets in distant regions of the galaxy, provided statistical insights into planetary formation and distribution, and demonstrated the incredible diversity of planetary systems. This method continues to expand our cosmic horizons, enriching our understanding of the galaxy's planetary population. This method, born from Einstein's theoretical work, has become a powerful tool in modern astronomy, allowing us to detect planets that would be impossible to find through other means. It stands as a testament to how pure theoretical physics can lead to practical applications in unexpected ways, helping us understand our cosmic neighborhood and the prevalence of planets throughout our galaxy. Each exoplanet detection method represents a vital piece of an intricate cosmic puzzle. Like instruments in a symphony, these techniques harmonize to illuminate the richness of our galactic neighborhood. Transit observations unveil planet sizes and orbital periods, radial velocity measurements provide planetary masses, astrometry maps, three-dimensional orbital architectures, and gravitational microlensing uncovers distant, otherwise invisible worlds. Together, these methods craft a comprehensive image of planetary systems, filling gaps that no single technique can address alone. The current state of discovery is nothing short of astonishing. Over 5,000 confirmed exoplanets populate our catalogues, with thousands more candidates awaiting confirmation. Hundreds of multi-planet systems have been identified, showcasing a diversity of worlds, from small rocky planets to massive gas giants. Exoplanets inhabit orbits and configurations once thought impossible, challenging our understanding of planetary formation and evolution. Looking ahead, we stand at the threshold of even greater discoveries. Next-generation telescopes like the James Webb Space Telescope are revolutionizing atmospheric studies, while the Roman Space Telescope promises groundbreaking microlensing surveys. The extremely large telescope will offer unmatched resolution, enabling detailed studies of planetary systems. Advancing technologies, from more sensitive instruments to artificial intelligence and machine learning, are enhancing our detection capabilities, paving the way for unprecedented insights. Potential discoveries may include Earth-like planets in habitable zones, biosignatures in exoplanet atmospheres, entirely new classes of planets, and perhaps even hints of extraterrestrial civilizations. The quest to understand exoplanets transcends scientific curiosity. It helps us contextualize our solar system within the cosmos, decode the processes of planetary formation, and search for worlds that might harbor life. This endeavor addresses some of humanity's most profound questions. How common are planets like Earth? Could life exist elsewhere? What extraordinary worlds remain undiscovered? If this exploration of exoplanet detection has sparked your curiosity, there has never been a better time to engage with the latest discoveries. Subscribe to Exploring the Universe for future adventures. Turn on notifications to stay updated on new findings, and share your enthusiasm with others who are equally captivated by our cosmic quest. Join our community of space enthusiasts in the comments section, and follow us on social media for daily updates and breaking news from the frontiers of astronomy. As we refine our methods and develop groundbreaking technologies, we edge closer to answering fundamental questions about life and the universe. Each day brings new revelations, reminding us that the universe is vast and our journey of discovery has only begun. Stay curious, keep your gaze on the stars, and join us for the next chapter in this extraordinary exploration. The countless worlds out there await discovery, and the universe promises to surprise us with its infinite wonders.